thank you for asking me to present this work. We are going to talk about initial condition ensembles, and the study aimed to figure out how many ensemble members are needed to achieve a quote-unquote good estimate of some metrics of extremes. The study has actually been published by now. It's in Earth System Dynamics. You see the reference down there, which also allows me to acknowledge my co-authors that are Kaylin Dorheim and Ruby from PNNL and Michael Wenner from Berkeley Lab. So let me start. Hopefully I can advance my slide. So the motivation was to try and estimate a priori what ensemble size provides a good estimate of both the force component and the internal variability for several extreme metrics. And what I mean by a priori is that we wanted to see if the availability of a much smaller ensemble than what we are used to think as large ensembles, that is an ensemble of 5 members, could allow us to say something a priori about the ensemble size needed to achieve a certain level of accuracy and precision in our estimates of these quantities. Of course, you know, what a good estimate means depends on your application. So when you do a statistical estimation, you come up with an error. The fact that that error is good or bad depends on what you're going to use your estimate for, right? So it is somewhat of a vague question to ask if I can determine the size of an ensemble that gives me a good estimate. But I hope in the next slides to show you how we went about making this question a little more answerable. So we are going to use 2 large ensembles that are available in the CLIVAR SMILES repository. You see the URL up there. So these are the famous lens ensemble with the CESM1. It has 40 ensemble members. It has been run under historical and RCP 8.5. It has the model has about a 1 degree resolution, and it covers actually a longer period than the one that you see here, 1950 to 2100. It actually starts in 1920, but we use a common period for these 2 ensembles. So I'm limiting it by starting from 1950. The second ensemble is by the Canadian model. The Canadian model has a coarser resolution, so 2 degrees, and a larger ensemble size, 50. Otherwise, same story, historical and RCP 8.5. So we are going to use the period between 1950 and 2100. The quantities. So when I talk about extremes in this presentation, of course, you can define extremes in many ways. What I'm going to use are metrics, indices that have been proposed in the community for many years now. There is literature about them. There are observations about them. And the metrics in particular that I chose are addressing extremes in maximum and minimum temperature and precipitation. These indices are usually either annual, like what we use here, or seasonal summaries based on daily quantities, daily maximum or minimum temperature or precipitation. And they are things like what you see here, like the hottest day of the year, where you take the maximum value of maximum temperature over the year, the hottest night, where you take the maximum minimum temperature over the year, or the coolest day or the coolest night, when you use the minimum of either maximum temperature or minimum temperature. And then you have indices defined in terms of amounts of precipitation. In this case, we take the largest amount of daily amount of the year, or the largest 5 consecutive days amounts of the year. And so these are the indices. Of course, given that we have a finite amount of time, and very short actually in this presentation, I'm going to show you results only for a couple of them. In the paper, we have results for all these. So the spatial scales, of course, matter when you talk about, precision and accuracy of an estimate. And we are going to look mainly in this presentation at grid point scales. And of course, in general, this is a stricter criterion than anything else, given a climate model. But in the paper, we actually started from global averages. We also looked at regional averages. Our results are fairly robust. So what I'm going to tell you applies to a whole range of scales. So let's start from the problem of estimating the force component of one of these quantities. So usually when we have an ensemble at our disposal, the force component is addressed by computing an ensemble mean. That's as simple as that. And of course, that ensemble mean will be as accurate as you have ensemble members. We are going to use a very basic result of statistics, which is when you are going to use a sample mean to estimate a quantity, the variance of that estimator, of that sample mean, is equal to the variance of the population divided by your sample size. And so if you have a criterion by which you can say, I don't want this variance to be larger than k, you fix k, you hopefully have an idea of what sigma square is, and I'll get to that in a moment. And therefore, you can derive what ensemble size you want to control the variance of your estimator. So what is sigma square? Of course, sigma square is the variance of your population. In this case, is your internal variability. Our hope was that we could get a good estimate of the sigma square only on the basis of 5 members. And what we do in particular is, since we want this variance to be time dependent, because we account for the fact that possibly the variance of the internal variability here changes over the course of a simulation, especially under high forcing like RCP 8.5, we choose the time that we are interested in studying. We take our 5 members, and then we use a 5-year window around that time so that we enrich the sample size by 5. And then we compute the sample variance, and we call that our sigma square. And then we decide, what ensemble size we are going to use if we have a certain criteria. But more precisely, or more concretely, let's say, let me see if I can just show you results on these maps. So what I've told you is that I can get a sense of the error of my estimate based on a certain ensemble size. I have an estimate of sigma square based on my 5 ensemble members. I can start thinking of n, my sample size, my ensemble size being 1, 5, 10, 15, 20, 25, 30, 35. And by that formula, I have a way of estimating what my error in computing my force component, that here I define at each grid point as the change in the metric by the end of the century compared to a historical baseline. So I have a way to guess what the error of that estimate is going to be on the basis of that formula. And then I have my real large ensemble that I'm using here as my truth. So I can compute the force component on the basis of all my ensemble members, in this case 40 or 50, and then I can compare what I actually get for the smaller sample sizes on the basis of my guess to the real error that I can compute by comparing my limited estimate to the full ensemble size estimate. So what these maps are showing you here are locations where my estimated error was below or equal between 0 and 100% of the real error. And when you see red instead, is a case where my a priori estimate failed. So I was overconfident using my 5 ensemble members to estimate the variance. And the point of this series of maps is to say, once I get to 20, 25 ensemble members, there are very few locations over this map where I see red. And these are based on 95% confidence interval, so you actually expect some locations to be red just by chance. This is true for this warmest night metric. It's also true for this precipitation-based metric. Again, you have a scatter of red points for 20, 25 ensemble members, where your error was underestimated. But we argue, and actually we compute the total size of this area, and it is within the 5% that you would expect by chance. So the results for this part, and of course in the paper we do this for all times of the simulation, for all the indices, for both models. And we find fairly robustly that we can use a small ensemble of 5 members to estimate the population variance. We can plug it into the formula. You can guess ahead what our error in the estimation of the first component is going to be as a function of sample size. And therefore, we can then decide what our sample size should be if we have an idea of the ceiling for this error that we want to protect us from. And this holds true not only, for the maps I showed you at the grid point scale, but also, and probably obviously, for more aggregated scales where you beat down the noise even more. So the other way we defined false component was a little more sophisticated from the statistical point of view. So these quantities are extremes. In particular, they are maximum or minimum values over the year. So you can use the individual values of these indices as a sample of values that can be fit by a generalized extreme value distribution, GEV. Once you do that, the GEV allows you to extrapolate, to say something about, for example, what is the 100-year event for the warmest night index? So what is the value of the warmest night that you expect only in 100 years if we were in a stable climate, or with 1/100 probability every year? So we choose different locations over the world because we want to sample different types of climate. And then what we do is we start taking increasing ensemble sizes. We choose a time in the simulation. In this case, I'm showing you the results for 2050. And for this time, let's say for 5 ensemble members, I'm taking the values of the warmest night at a certain location. Here I'm showing you a location in northern North America. I actually get 25 values, not only 5, because I'm using that 5-year window around 2050. And on the basis of those 25 data points, I can estimate a GEV, and I can determine what is the 5, the 10, the 20, the 25, or the 50, or the 100-year event that I'm showing you here. So let's focus maybe only on this 100-year event plot. What the red dots here are the central estimates that I derive for the 100-year event. I'm sorry, this is my mouse that is misbehaving. The red dots are the central estimates of this 100-year event based on a GEV that is fitted for increasing sample sizes. So for an ensemble of 5 or 10, 15, 20, 25, 30, 35, as it's indicated by the x-axis that I hope you can read. The pink envelope is the uncertainty around that estimate. And the blue dots are estimates of these 100-year event that are based only on gathering those data points, not fitting the GEV, but just ranking them and taking the value that leaves, only 100 of the probability to its right. So the point here is that I can use the full ensemble, in this case 40 ensemble members, to derive a central estimate and an interval that I call the truth. And those are marked by those horizontal lines, and also the last dot that you see on the right-hand side of each plot. So those are my so-called truth. And then I'm seeing that both the central estimate and the confidence interval are kind of stabilizing around the central line and the range of the uncertainty once I get to 20, 25, again, ensemble members. And that is true across the board. If I scroll one additional slide, you see that it's true also of the precipitation metric. The conclusion here, and of course I cannot show you, but we did it for all those locations. We did it not only for 2050, but for various times during the simulation. And we find that in general, this magic number of 20, 25 ensemble members seems to satisfy this stabilization that we require of our estimates across the board. Now, when we look at those blue points, if I go back, one could argue that 2025 produces an empirical estimate that is within the confidence interval, so one may be satisfied by that. But I argue that the variability of those estimates is a little larger for the blue points than the red points, and also the other disadvantage is that the blue points are derived by a method that doesn't really allow you to say much about the uncertainty. So I think I'm getting close to 20 minutes, but what I want to mention, at least in words, and then if we have time, I can show you some plots, is that we also address the problem of estimating the internal variability of these quantities, not just the force component. And so, first of all, what I define as internal variability is simply the standard deviation of the ensemble, so the inter-member variability. And again, we are asking how many ensemble members do we need to get a good estimate of the internal variability. And of course, again, we call the true internal variability what we get from the whole ensemble, the 40 or 50 member ensemble. We conducted this analysis at the grid point level, and we asked actually two questions. The first question is, can I estimate accurately the internal variability at a given time during the simulation? And the second question, which has a slightly different answer, is, can I estimate accurately a change in internal variability between two times during the simulation? And as you can imagine, the answer is a little different, because in the second case, you are estimating a difference between two random quantities rather than just trying to estimate a single random quantity. So you may have more noise going on. So we actually find that between 5 and 10 ensemble members, again, if you add that 5-year window around, each time that you do this, and so you enrich your sample size that way, seem to be sufficient to estimate the size of the real inter-member variability. If you apply, the usual F-test, which is the standard way in statistics to define, statistical differences between variances. Now, when you ask, though, about the number of ensemble members that you need to detect a change in the variance, in that case, and especially for the precipitation metrics, it turns out that you need more ensemble members. Again, the magic number reappears. 20, 25 ensemble members seem sufficient to pinpoint changes at the grid point level between times in the simulation that your full ensemble would signal are different. So the conclusions of the whole talk, and then I either stop or I go back to show you the actual result for the variability, is that it is possible to estimate a priori with good accuracy what ensemble size is needed in order to estimate signal and noise characteristics of several metrics of extreme temperature and precipitation. We did this analysis for 2 different models with 2 different resolutions for a large range of radiative forcing or warming levels, and several metrics of extremes that include daily maximum, minimum temperature and precipitation. And we find that we can talk about outcomes that are fairly robust across all these variations in the analysis. And our main conclusion is that 25 members seem to meet our various estimation goals. And if I had to define these goals in a word, I would say they do as well as the full 40, 50 member ensembles according to the metrics that we decided to study. And this is true both for identifying the forced response and for estimating internal variability at the grid point scale, and for both temperature and precipitation metrics. Of course, I showed you that for some 20-25 members is plenty. We can do away with many less. Of course, though, you can argue the right answer to the question of how many ensemble members you need depends on what you use this ensemble for, what you're out to estimate and what your tolerance for error is. So you may argue that you have just wasted 20, 22 minutes of your time because we are here to answer a question that doesn't really make sense to ask. But at least for this application, for this type of metrics, the idea that we can actually get away by running a 25 member ensemble rather than a 40, 50 member ensemble could be useful when we design experiments and we try to explore sources of uncertainty that are, other than just initial condition uncertainty, and in particular initial conditions in the atmosphere. So that's my goal for this talk. So if there are questions, I'd be happy to answer them. If you want me to fill in more minutes, I can go back to the variability results, but I would rather give a chance to people to ask questions. Thank you for your attention.